projected simultaneously on the same component, which is again under fitting. Now, one of the most important things that you need to observe, always whenever there is a possibility of combined loading, we will always make use of theories of failure, right? So two most widely accepted theories of failure are maximum principal stress theory, which is more often used for ductile brittle materials, and the second widely used theory is maximum shear stress theory, which is more applicable for ductile materials. So whenever we are designing a component, for the design to be safe, these two criterions are to be met. The first one is the maximum principal stress induced in the component should be less than or equal to the allowable stress, right? Allowable stress is yield strength of the material divided by factor of safety, or ultimate strength of the material divided by factor of safety, based on whether the material is ductile or brittle. Sigma 1 is the maximum principal stress induced in the component, right? If the maximum principal stress induced in the component is well within the allowable stress, then the design is safe. Or if we are making use of the maximum shear stress theory, the maximum shear stress induced in the component should be less than or equal to the allowable strength in shear. So if these two conditions are satisfied, then the design can set to be safe. So whenever we are trying to solve the problem, we need to ensure that the stresses that are induced in the component are well within the allowable stress, right? This is the first thing that you need to remember. And secondly, you know that whenever we are making use of ductile materials, we will be making use of Soderberg's equation. Whenever we are making use of brittle materials, we will be making use of Goodman equation. For the purpose of illustration, let us consider Soderberg equation. Right? What is Soderberg equation? It states that the fatigue stress concentration factor Kf sigma multiplied by the stress amplitude sigma A divided by KSR, KSZ, KLD times the endurance limit of the material plus sigma m, that is the mean stress, divided by yield strength of the material is equal to the reciprocal of factor of safety. This is what Soderberg equation states. Now let me multiply this equation by sigma y. So what will happen if I multiply this equation by sigma y? I will get an equation of the form Kf sigma multiplied by stress amplitude divided by KSR, KSZ, KLD, right, into sigma minus 1, the entire thing multiplied by the yield strength of the material plus sigma m by sigma y into sigma y. So thereby this will be just sigma m is equal to sigma y by factor of safety. This is equal to sigma y by factor of safety, right? This is the equation that we have. The magnitude of the stress that is obtained from the first half of the equation is called as equivalent stress induced in the component. What do we call it? It is called as equivalent stress induced in the component, right? So what do we mean by it? So whenever we are encountering a combination of different type of forces on the component will be subjected to different type of stresses, right? Suppose if the component is subjected to a combination of axial and bending loading, then it will be subjected to axial stress as well as bending stress. Suppose if it is subjected to a combination of bending and torsion, then the component would be subjected to shear stress as well as bending stress. Now, this is what it means. So whenever we are making use of or whenever we are designing components under fatigue loading, we will determine the value of equivalent stress induced in the component first. Then we will make use of the same equation So it's the same magnitude of stress in the expressions for either maximum normal stress theory or maximum shear stress theory, and then using which we can determine the unknown quantity which is present in the equation. That is the idea. Now, what I have stated is valid if the component is subjected to normal stress. Now, the direct axial stress is there, the equation that is present here is valid. Let us call this as equation 1. The equation 1 is valid when the component is subjected to either axial force or bending force. Now, what will happen if the component is subjected to shear force? It is very simple. You replace every sigma that is present in the equation by tau, right? So, if the component is subjected to shear stress, this will be sigma k of sigma into stress amplitude divided by KSR, KSZ, KLD times sigma minus 1. So always remember sigma minus 1 tarane tau minus 1 anta one expression illa. There is no such expression. Why? Because whenever we are determining the endurance limit of the material, the component is basically subjected to both bending and shear. So thereby there is no such thing called sigma minus 1 tarane. There is no such thing called tau minus 1. Remember it. This multiplied by tau I plus the mean shear stress is equal to tau I divided by factor of safety, which is equal to tau equivalent. This is the equivalent shear stress induced in the member. Let me call this as equation 2, right? So the use of this equation, we can best illustrate it by making use of problems. So before we begin these problems, so let us understand. So whenever we are making use of maximum principal stress theory, whenever we are making use of maximum principal stress theory, the formula to calculate the maximum principal stress induced in the component, that is sigma 1, is given by 2. So here sigma equivalent by 2 divided by plus square root of sigma equivalent by 2 the whole squared plus tau equivalent squared. Correct? This is the expression for determining the maximum stress induced in the member, maximum principal stress induced in the member. Similarly, how do we calculate the maximum shear stress induced in the component? The maximum shear stress induced in the component is given by this term of the equation, which is nothing but square root of sigma equivalent by 2 the whole squared plus tau equivalent square. So these three equations or these four equations should be kept handy whenever you are trying to solve problems on fatigue when the component is subjected to combined load. So now let us try to solve a problem. Let us try to illustrate the concept by solving a problem. You take down the problem. A steel shaft is made of SAE 1045 steel with this oil quenched is subjected to a repeated bending moment of 600 Newton meter and a reversed twisting moment of 600 Newton meter. Determine the diameter of the shaft. Based on a factor of safety of 1.8. Based on factor of bending, this is 500 Newton meter. I'm sure change ಮಾಡ್ಕೊಳ್ಳಿ problem ಅಲ್ಲಿ 500 Newton meter ಅಂತ ಕೊಟ್ಟಿದೆ, right? So So this is the problem at hand, right? So they have also given the yield strength of the material. They have also given the yield strength of the material. Let us sigma y to be 425 MPa. This is 425 MPa. And its endurance limit sigma minus 1. Endurance limit sigma minus 1 is 365 MPa. So this is the problem at hand. ಬರ್ಕೊಂಡ್ರ ಪ್ರಾಬ್ಲಮ್? Did you take down the problem? Can we begin with the solution?
Yes, sir.
Sir, again given now.
Now let us ಯಾವುದು ಮೆಟೀರಿಯಲ್ ಪ್ರಾಪರ್ಟಿ ಅವರೇ ಕೊಟ್ಟಿದ್ದಾರೆ, ಸಿಗ್ಮಾ ವೈ ಮತ್ತೆ ಸಿಗ್ಮಾ ಮೈನಸ್ 1. They have given the problem itself. Now let me try to diagrammatically represent the problem at hand. So what we have is a shaft. So the shaft would be somewhat like this. There is no stress, there is no presence of stress concentration because no such data has been mentioned. So this will be a prismatic shaft, right? This is the shaft that we are having, right? This is the problem at hand. So what is that we need to determine? We need to determine the diameter of the shaft. So whatever equation that we make use of or that we develop until the end of the problem, it will be in terms of d. So d is the diameter of the shaft. So the shaft is subjected to a repeated bending moment of 500 Newton meter. So how is that? This is the bending moment, right? What do you mean by the bending moment being repeated? Repeated antandre no, always remember, repeated indicates it is varying from 0 to a certain value. So this is subjected to the bending moment. So the maximum bending moment is 500 into 10 to the power of 3 Newton millimeters, and the minimum bending moment is 0 because the load is given to be repeated. This is one force that is acting on the component, and the second type of force that is acting on the component is a twisting moment. The second type of force that is acting on the component is a twisting moment. They have told you that the twisting moment is reversed in nature. The twisting moment is reversed in nature. So what do you mean by reversed? So the magnitude remains the same, whereas the sign of the magnitude is changing. So thereby mt max, that is the maximum twisting moment, is 600 into 10 raised to 3 Newton millimeters, whereas the minimum twisting moment, mt minimum, is -6. So ಇದು ಹೇಗೆ ಬರ್ಕೊಂಡ್ವಿ ಅಂತ ಅರ್ಥ ಆಗಿದೆಯಾ? ಅರ್ಥ ಆಗಿದೆಯಾ ಹೇಗೆ ಬರ್ಕೊಂಡ್ವಿ ಅಂತ? So I'll assume that you have understood. So now ಸೊ ರಿಪೀಟೆಡ್ ಬೆಂಡಿಂಗ್ ಮೂಮೆಂಟ್ ಅಂತ ಕೊಟ್ಟಿದ್ದಾರೆ, ಹೌದಾ? ರೆಡ್ ಕಲರ್ ಲೈನ್ ಅಲ್ಲಿ ಅಂಡರ್ಲೈನ್ ಮಾಡ್ತಾ ಇದೀನಿ ನೋಡಿ. ರಿಪೀಟೆಡ್ ಬೆಂಡಿಂಗ್ ಮೂಮೆಂಟ್ ಅಂದ್ರೆ ಏನು? ರಿಪೀಟೆಡ್ ಮೀನ್ಸ್ ದಟ್ ದಿ ಲೋಡ್ ಇಸ್ ವೇರಿಯಿಂಗ್ ಫ್ರಮ್ ಎ ಮಿನಿಮಮ್ ವ್ಯಾಲ್ಯೂ ವಿಚ್ ಇಸ್ 0. ದಿ ಮಿನಿಮಮ್ ಲೋಡ್ ಇಸ್ 0, ಮ್ಯಾಕ್ಸಿಮಮ್ ಎಷ್ಟೋ ವ್ಯಾಲ್ಯೂ ಇದೆ. ಇವಾಗ 0 to f maximum ವೇರಿ ಆಗುತ್ತೆ. ಅಗೇನ್ ಇಟ್ ವಿಲ್ ಕಮ್ ಬ್ಯಾಕ್ ಟು 0, ಅಗೇನ್ ಇಟ್ ವಿಲ್ ಗೋ ಬ್ಯಾಕ್ ಟು f max and so on. The cycle continues. So repeated ಅಂತಂದ್ರೆ always minimum force is 0. So here the minimum bending moment is 0, ಮ್ಯಾಕ್ಸಿಮಮ್ 500 ಇದೆ. ರಿವರ್ಸ್ಡ್ ಅಂದ್ರೆ ಏನು? ಮ್ಯಾಗ್ನಿಟ್ಯೂಡ್ ಸೇಮ್ ಇರುತ್ತೆ ಬಟ್ ಸೈನ್ ಚೇಂಜ್ ಆಗುತ್ತೆ. ಒಂದು ಕೇಸಲ್ಲಿ ಪಾಸಿಟಿವ್ ಟ್ವಿಸ್ಟಿಂಗ್ ಮೂಮೆಂಟ್ ಇರುತ್ತೆ, ಇನ್ನೊಂದು ಕೇಸಲ್ಲಿ ಇದು ನೆಗೆಟಿವ್ ಟ್ವಿಸ್ಟಿಂಗ್ ಮೂಮೆಂಟ್ ಇರುತ್ತೆ. ದಟ್ ಇಸ್ ವಾಟ್ ದಿ ರಿವರ್ಸ್ಡ್ ಟ್ವಿಸ್ಟಿಂಗ್ ಮೂಮೆಂಟ್ ಮೀನ್ಸ್. ಸೊ 600 ಮ್ಯಾಕ್ಸಿಮಮ್ -600 ಮಿನಿಮಮ್. ಅರ್ಥ ಆಯ್ತಾ?
Yes, sir.
Okay, fine. Now, since the data is clear, now we need to make use of a design equation. So, in case ಅಲ್ಲಿ what will be our design equation? ಯಾವ equation ತಗೋಬೇಕು? ಈ ಕೇಸಲ್ಲಿ ಸೋಡರ್ಬರ್ಗ್ equation is our design equation. ಹೌದಾ? Because the material is ductile, Soderberg equation will be our design equation. So, what we need to do is we need to make use of equation 1. So one of the most important thing that you need to observe here is, since the component is prismatic, ಅಂದ್ರೆ ಏನು, change in cross section ಎಲ್ಲೂ ಇಲ್ಲದೆ ಇರೋದ್ರಿಂದ ಕಾಂಪೊನೆಂಟ್ ಅಲ್ಲಿ, the value of kf sigma need not be taken care of. Kf sigma will be equal to 1 because there is no change in cross section, which translates to there will be no stress concentration in the component. So a kf sigma bitbittu you note down the remaining equation. So what will be the design equation? Design equation is Soderberg equation itself, because the component is ductile in nature. So this is sigma A divided by KSR KSZ KLD times sigma minus 1, the whole thing multiplied by sigma Y plus sigma M is equal to 1 by factor of safety. ಯಾವ್ದಕ್ಕೆ? This is valid for bending load, right? So a component is subjected to a combination of bending and shear. So first ಏನ್ ಮಾಡ್ತೀವಿ, let us consider bending force. Let us make use of this equation and let us calculate the equivalent stress induced in the component. So let us calculate the equivalent stress induced in the component. So in order to do it, let me calculate the value of the maximum bending stress induced. How do you calculate the maximum bending stress? Sigma B max. Sigma B max in this case will be nothing but sigma max, right? So how do you calculate sigma B max? The component is circular in cross section. So the formula to calculate the bending stress is 32 into MB max divided by pi d cube, right? So what is it? 32 into the bending moment was 500 into 10 raised to 3 divided by pi d cube. Can someone calculate it and tell me the simplified expression for sigma B max? 32 into 500 by pi ಎಷ್ಟು ಬರುತ್ತೆ? Some value multiplied by 10 to the power of 3 by d cube MPa.
Sir, 50929
50929 into
by
10 to
D
the
cube. By D cube.
into 10 to the power of 3 ಬಿಟ್ಟು ಹೇಳ್ತಾ ಇದೆಯಲ್ವಾ ನೀನು?
ಹಾ ಸರ್.
50929
ಇಲ್ಲ ಸರ್, ಮಲ್ಟಿಪ್ಲೈ ಮಾಡೆ.
509.29 ಅಲ್ವಾ? 509.29 into 10 to the power of 3 ನಾ?
ಹೌದು ಸರ್.
Okay, fine. So similarly, since the load is reversed, sigma B minimum is 0. ಹೌದಾ? ಯಾಕೆ? Because it is a reversed load. So this is 0 MPa. Now, making use of these two equations, let me calculate the mean stress. What is the formula to calculate the mean stress? Sigma M is equal to sigma max plus sigma minimum by 2. So that is 509.929 by 2. So ಎಷ್ಟು ಬರುತ್ತೆ? Upon substitution, sigma M, that is the mean stress induced in the component, will be 254.5. 250.45, 4.5 something ಬರುತ್ತೆ. So it is roughly 254.5 into 10 to the power of 3 by d cube MPa. ಕರೆಕ್ಟಾ ವ್ಯಾಲ್ಯೂ?
ಸರ್ ಅದು ಸಿಗ್ಮಾ ಬಿ ಮ್ಯಾಕ್ಸ್ 5092.9 ಅಂತ ಬರ್ತದೆ ಸರ್ ನನಗೆ.
592.9
5092.9
into 10.
Yes sir, yes sir.
ಸರ್ ಪಾಯಿಂಟ್ ಆಚೆ ಬರ್ಬೇಕಷ್ಟೇ 2 ಆದ್ಮೇಲೆ.
32 into 500 into 1000 divided by 3.1416 divided by 1000. 5092.29. Okay.
ಹೌದು ಸರ್.
Okay. So ಹಾಗಿದ್ರೆ ಇದು ಚೇಂಜ್ ಆಗುತ್ತೆ ನಿಮ್ಗೆ ಒಂಚೂರು. This is 5092.95. 0.95 ಬರುತ್ತೆ. ಸೊ ಹಾಗಾದ್ರೆ ನಿಮಗೆ ಮೀನ್ ಸ್ಟ್ರೆಸ್ ಎಷ್ಟು ಬರುತ್ತೆ? 2545 46 roughly. Okay, this is the mean stress. Since the load is repeated in nature, repeated load ಆಗಿರೋದ್ರಿಂದ ಅಂದ್ರೆ ಸಿಗ್ಮಾ ಮಿನಿಮಮ್ 0 ಇರೋದ್ರಿಂದ, since the value of sigma minimum is 0, sigma a ಮತ್ತೆ sigma m both will have the same value. ಹೌದಾ? Stress amplitude, since the right hand term of the equation is 0, the value of stress amplitude will be same as sigma m. So it will also be equal to 2546 into 10 to the power of 3 by d cube. So remember this is what we need to do. So again you need not calculate it, direct ಆಗಿ mention ಮಾಡಬೇಡಿ ಅಷ್ಟೇ. So this is what we have calculated. So next ಏನ್ ಮಾಡಬೇಕು? What is that we need to know? The values of sigma minus 1, the values of sigma minus 1, sigma y are known. These two values are known. You have calculated the values of sigma a as well as sigma m. ಇವೆರಡನ್ನು ನೀವು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿದ್ದೀರಾ. ಸೊ ನೆಕ್ಸ್ಟ್ ಏನ್ ಮಾಡಬೇಕು ಅಂತ ಹೇಳಿದ್ರೆ, we need to determine the values of the endurance limit modifying factors. These values need to be determined. So how do you determine it? Make use of equation 5.19, right? So make use of equation 5.19. Can you tell me the values of KSR, KZ and KLD? What will be the value of KSR? KSR in madira again, based on the surface finish, you will decide the value of KSR. So what we need to do, let us assume that it is smooth mill cut. So assuming that it is smooth mill cut, what is the surface coefficient? ಎಷ್ಟು ಬರುತ್ತೆ ನೋಡಿ?
0.87.
0.87, good. Then what about KSZ? KSZ ಅಲ್ಲಿ ಏನು? Diameter of the component ಗೊತ್ತಿಲ್ಲ, right? We do not know the diameter of the component. Let me assume that the diameter of the component is in between 10 mm and 15 mm. ಯಾಕೆ? In order to calculate the size factor, we need to know the value of the diameter. So now we do not, that is what the problem is. We need to calculate the value of diameter. So let me assume that the size is in between 10 to 50 mm. Okay. So what will be the value of KSZ then? 0.9 alva?
Yes, sir.
Okay. So lastly, we need to calculate the load factor. So what will happen if the load is bending in nature? Bending in nature, what is the formula to calculate? What is the load factor? 1, right? Correct?
Okay.
Yes, sir.
Okay. So now what we shall do, we shall substitute all these values back in equation star, right? You substitute all these values in equation star, which is the Soderberg equation for bending load. So you consider this equation. So this is equation star. You substitute all the values here and tell me the simplified expression in terms of d cube. ಎಷ್ಟು ಬರುತ್ತೆ? ಸೊ ಇಲ್ಲಿ ಏನ್ ಮಾಡ್ತೀರಾ? ಫಾರ್ ದ ಟೈಮ್ ಬೀಯಿಂಗ್ ಲೆಟ್ ಅಸ್ ಕೀಪ್ ಅಸೈಡ್ 1 by factor of safety. 1 by factor of safety ನೀವು ಬಿಟ್ಬಿಡಿ in the sense that you keep it aside, you substitute this and tell me the value of sigma eq. What will be the value of sigma eq? Something divided by d cube ಬರುತ್ತಲ್ವಾ ಇದು? Yeah, something divided by d cube plus sigma m is, what is sigma m? Sigma m is 2546 into 10 to the power of 3 by d cube. 2546 into 10 to the power of 3 by d cube. Idiಷ್ಟನ್ನು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿ, tell me the value of sigma eq. So guys, you solve this till here and be ready. since the principal is going to address you guys now.
ಸರ್ ಯಾವ
we shall
equation ಸರ್ ಇದು?
ಸೋಡರ್ಬರ್ಗ್ ಈಕ್ವೇಶನ್ ಕಣ, ಇಲ್ಲಿ ಈಕ್ವೇಶನ್ ಸ್ಟಾರ್ ಇದೆಯಲ್ಲ, ಸೋಡರ್ಬರ್ಗ್ ಈಕ್ವೇಶನ್ ಕಣ, ಈಕ್ವೇಶನ್ ಸ್ಟಾರ್ ಹಾಕಿದೀವಲ್ಲ ಅದಕ್ಕೆ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡೋ.
ಸರ್ ಓವರ್ ಆಲ್ ಆನ್ಸರ್ ಎಷ್ಟು ಬರುತ್ತೆ?
ಓವರ್ ಆಲ್ ಆನ್ಸರ್ ಚೆಕ್ ಮಾಡೋಣ. ಇವಾಗ ಇವ್ರು ಏನದು ಪ್ರಿನ್ಸಿಪಲ್ ಅಡ್ರೆಸ್ ಮಾಡ್ತಾ ಇದಾರೆ ನಿಮ್ಗೆ. ಸೊ ಇಸ್ ರೆಡಿ ಇಟ್ ಸೀಮ್ಸ್. ಸೊ ವಿ ಶಲ್ pause for now. We shall continue solving this problem in the next class. Madhu sir ನಿಮ್ಗೆ